Bene,
Well, this is a wonderful opportunity here at Enoforum for us to start telling you about very promising results of a research work that has been going on for years now. It is a project, a research project, whereby we managed to develop a new material. I talk about functionalized mesoporous silica with the intent of having protect stabilization of wines. My name is Gianni Triulzi. I work at Enartis, where I am R&D director. I will take the floor together with Matteo Marangon from Padua University. I will focus on three things. Protein instability. I will tell you briefly what it is, what is to blame for that, and why it is a challenge. Then I will talk about the current situation, that is protein stabilization today. What can we use? And I will see whether these instruments are in line with the needs of the sector. I will then conclude by talking about the future, and I will tell you about this project and the results we have obtained so far. So what is protein instability? Very briefly, it is the presence of turbidity, of this cloud appearance. Here in the beginning, you have a clear wine, which is no longer clear in the end. This is something that happens, unfortunately, and this goes especially for the shipping phase. Cloudiness is a major problem. What is it? If you have a look in the microscope at the cloudy wine, you see that a deposit can be formed, and this does not have a specific shape or form, and it is amorphous. The protein destabilization process starts with the creation of protein compounds that exit the solution, produce turbidity or cloudiness over the course of time. This changes over the course of time. There is an aggregation of compounds. There is an increase in their weight. They sediment and create a deposit. This is the process. We talk about proteins. We talk about protein instability. What proteins are we talking about? Not all of them, of course. There are specific categories. These specific categories is the category of PR proteins, pathogenesis-related proteins. It is proteins that are used by the plants to defend themselves against several stress types. You have chitinase and TLPs, which is a complex compound group. We can state for sure today that all unstable proteins come from the grape, and if there is a high protein instability, their quantity is 0.3 grams per liter, which is a lot, and which can account for a lot of cloudiness, which means that consumers see that cloudiness. These are compounds that are present in a colloidal dispersion, not in a perfect solution, which means that they are in a sort of precarious situation. They are not huge. The molecular mass, the range is 20 to 30 kilodaltons, always a positive charge vis-à-vis the pH of wine. They are featuring both hydrophilic and hydrophobic characteristics in the same molecule. So this is a very important feature, especially when we need to consider their reactivity. let's have a look at how they are made. Well, proteins are chains of amino acids. You can indeed imagine a linear chain, but nature is not as simple as that, unfortunately. This is what we think could be a 3D structure of chitinase. So you see that it is a globular protein with repeated portions, but a complex structure. And the same goes for the other categories, that of TLPs. There again, the structure is globular with repeated portions, but it is a very difficult structure to understand. And yet you increasingly understand more thanks to the fact that an increasing number of people work on this. Professor Marangon is one of them. And here you see this very same molecule studied in terms of its hydrophobic features. You have this form, and you can expose parts to portions with affinity to the solution to see how it behaves. It is in blue. It is an colloidal dispersion, this molecule, and so that has to be taken into account. But it is not entirely blue. It also has hydrophobic parts, which are reddish on the slide. It is reactivity sites that trigger phenomena that we see at the end of the process with the onset of cloudiness. So we talked about these big polymers. They are sort of protein clumps. Imagine you have the external part of this clump with this ball of proteins, and it is a fairly organized structure if you have a yarn in it. But what about the same ball of yarn which is put under stress? You unwrap the ball, and what happens is this. You can have a higher formation of knots, and there are many balls of yarn, say proteins. So there is an increasing amount of confusion that translates into our deposit. This is the unfolding process, which tells us why protein stability is still a huge problem today. A good stability situation after stress comes into the picture changes entirely, and this opens up new scenarios. In addition to that, you should also consider that these balls unfold and then fold again in a way. So I hope that that was a clear and understandable description of the phenomenon that causes turbidity. The phenomenon, of course, needs to be managed. How can we manage instability of proteins today? There are several instruments which I put into two main categories. Some are useful, but do not entirely solve the problem. We have tannins, for sure. They have a strong negative charge, and they react with proteins, which are always positive charged. And so they help, but they not solve the entire problem. The same goes for protease, aspergillopepsin, which is authorized for winemaking now. and it does something in function of the condition of the protein. If the protein is highly exposed, it works well. If it is not, less so. But we have a full module about that later on, so I will stop here. There are additional options, and there is specifically one which I'm sure is something that you all thought about, and it is bentonite, and bentonite, and bentonite. So basically, we have one possible solution. Bentonite is a silicate of aluminium rich in iron and additional cations, magnesium, calcium, sodium. It is a silicate which, depending on the hydration of the cations it contains, puts a distance between these layers of silicate, and you have a swelling of the bentonite. There is an increase in volume. There is a volume whereby there is a release of cations, and these leaves of silicate detach. It is available on the market also in a powder form and others. This is what you see there. This is bentonite. Does it work? Indeed it does. And yet, let me add a couple of things. It is non-specific, the sieve function. It is effective due to its very intense electric charge. And yet, even though it works, is bentonite in line with the needs of the sector? Using it, is it something that makes producers happy? And what does it mean to be in line with the winemaking needs of the sector of today, of course? Is this practice a precision enology practice? Can we impact only on that, leaving all the rest unaltered? Is it sustainable? Is it a lean process? Well, the answers are no to these three questions. It is no precision enology because adsorption is generic, and adsorption, by the way, and the usage of bentonite causes a major loss of wine. Based on estimates, between 3 and 5% of treated wine is lost. 3 to 5%, if you consider it globally, means that approximately 4-5 million hectoliters per year are lost due to this treatment. Is it sustainable? Well, the product is used and then it has to be disposed of. Is it a lean and fast process? Not really, because you need to prepare, you need to apply a sedimentation process, so there is waiting time. Let's now have a look at the main topic of this contribution. What is it that we did in order to make a step forward? And we started here working on a new material, which is functionalized mesoporous silica. It is silica. Bentonite falls within the same category. So we kept an approach which focuses on the same type, let's say, of material with similar features. The material, though, has been tailored, standardized, and made to remove unstable proteins. Here you see basically the structure. It is fairly special. There is an incredible porosity. This is the material before it's being used. This very high porosity level features the presence on the surface of chemical hooks, as I called them, which are functions, as a matter of fact, peculiar functions which are capable of interacting with the protein which enters into the pore, into the material. And the protein enters into the material. There are these sort of hooks that retain the protein. This is the material after the process. The wine has been stabilized in terms of its proteins. Now you will see further pictures. It is silica, as I said. So the information actually does not tell much because, you see, it is white. It comes in the form of powder. The average dimension of particles is 30 microns. And yet there are two crucial features here in terms of the effect they produce. Their very high porosity, which I mentioned earlier on, is the first one. Here you have a picture that we created, or that we obtained with the TEM microscope, 80,000 magnifications. You see this. We see here very clearly that there is a huge quantity of pores that sort of become canals, sort of tunnels. This special structure entails that there is an incredible surface in the material. In that, if you read, 1 gram of the material has an active surface exceeding 600 square meters. I say active surface because functions are present on that surface. They fall within two categories: acidic, with negative charges. Proteins are always positively charged to the pH of the wine, and then hydrophobic functions. You possibly remember earlier on when we talked about the hydrophobic areas of the molecules. So this makes this material highly specific in terms of protein stabilization. The porosity is very close to the unstable molecules, and it has chemical hooks which have been designed specifically to counter the defects of unstable proteins. So you understand very well that we talk about a very high degree of innovation. This is a new material. It is indeed new in all its features. Now, is it in line with the winemaking needs that we have? Let's go back to what we said earlier on when we talked about the functionalized mesoporous silica. Is it winemaking winemaking? Indeed, it is. The loss of wine is either negligible or absent, depending on the way you apply it. Is it sustainable? Indeed, it is. It can be regenerated. And is it a fast process? Indeed, it is, because this material makes it possible to have an inline treatment, which we called stabilizing filtration, protein stabilization filtration. So, of course, here the picture is very different from what we said about bentonite. So functionalized mesoporous silica is in line with the needs of the sector. It has been designed on purpose to meet those needs. How is it used? How can we use it? There are two possible ways, especially non-continuous process. It is added to the tank and then sedimentation takes place. But this is not what we focus on. I told you in the beginning, it is a research project, and there is a very strong development in progress. It is a research project, so we are still working on this, but we work on inline stabilization by means of filtration. which means that the material is going to be used as follows. You have a tank with unstable proteins, filtration through the material, and then a stable tank, objective and goal met. That is what we go for. We talked about a new material and a new application. Of course, you need to be authorized to produce this. This project started a number of years ago. We then started with OIV, the process to get the authorization in 2022. And the practice for the treatment of wine with functionalized mesoporous silica was authorized. It was in 2024. You see the code of the document on the slide, and the recommendation by OIV is admitted. Have we covered everything? Indeed, we haven't. What are the next steps? We still need to focus on the treatment of the juice, and we need to conclude also the practice and the proceedings for the monography of the material. These two parts are still in progress. The authorization phase is 5 out of 8, which means the second last phase. There is a last one, an additional one, and then the process is complete. I have told you about the material. I have told you about the possible application and the authorization. Does this material work? It does. So let's have a look at the effectiveness. I would like to give the floor to Professor Marangon to tell you about this. He will go into the details of these two aspects. Thank you. Thank you, Gianni, and good morning to you all. It is always a great pleasure to be here with you at Enoforum. The cooperation started a few years ago, and we were asked about the fact that functionalized mesoporous silica is or is not effective. I will share with you data about the performance, therefore, of this new material, of SMF. Clearly, people working in the sector, when told about a new technique, immediately ask whether the technology or the technique is effective, whether it works as well as bentonite. Then there are additional questions coming from winemakers, and they pertain to additional aspects. First of all, specificity is an issue. Are there side effects? Is there an impact on the chemical composition of wine? There are also other factors which are decisive and which will determine whether this solution is marketable, successful or not. And one is sustainability, which is at the center of everybody's interest. Then practicity, meaning how easy is it to use it, and then competitiveness. Is it expensive? These are the 5 areas that I will focus on today, and I will try and answer a number of questions that, of course, arise when a new technique is presented. Is it effective or is it not? How can we assess that? There are 2 main ways when talking about protein stability. First, we look at protein removal following the treatment. Second, the heat stability test. You induce stress so that the unstable proteins mentioned by Gianni denaturate, aggregate, and form cloudiness and a sediment in the end. This is a technique that we use on a daily basis. It is based on a reverse phase HPLC system, whereby we analyze TLPs, which are the peaks that you see in the chromatogram, and the chitinase, which are peaks after 20 minutes of the analysis. In this specific analysis, you see data about Friulano, a variety wine from 2019, with these beautiful peaks of both groups. Then treated with SMF or with bentonite. The former is in red, the latter in green. You see that peaks, the treatment is much lower, and the protein, therefore, instability is lowered, and we can calibrate with a standard protein and calculate that.
4-5 slide. Quindi calano le proteine, però sappiamo dalla letteratura.
So there is a reduction in proteins. We know that protein content does not necessarily correlate with stability or instability. And knowing that proteins have diminished does not tell us that proteins are unstable.
Diciamo all'interpretazione numerica del grafico che vi ho appena fatto vedere, quindi sempre lo stesso.
Going back to the interpretation of the chart, always the same one, you will see that the one, considering the protein concentration, we have a sample that contained 7.3 subdivided with a total of 42, subdivided into 32.1 TLPs and 10 chitinases, and then hot test was run 80 degrees C for 30 minutes, 2 hours at room temperature, and the instability is 7.3. So it is unstable, but not strongly unstable for this type of wine. Now, with 20 grams hectoliter of sodium bentonite or 25 grams per hectoliter of silica, we had managed to stabilize the wine at 1.1 and 1.2 respectively. So similar amounts of either bentonite and silica, and that removed chitinase and tomatin with a significant drop in total proteins. In this case, it worked with one wine, although one might object that 7.3 in instability it does not mean a very unstable wine.
In questo caso si trattava di un'erba luce.
Here we passed on to a different region with erba luce. The heat test, especially done with tannins, whereby you add tannins during heating, the value was 68, with the classic heat test 0.7. So unstable, but not that much when compared to the previous one. We see here that we added 60 grams per hectoliter of bentonite and of SMF, same dose, and we obtained the stabilization in the traditional heat test, which are similar for both groups. And in the heat test with tannins, we managed with SMF to stabilize the wine, which was not the case with bentonite. This is another variety, Sauvignon Blanc Friuli. Here you see the table with total protein, very high value, 260 in the sample, and high chitinase, also high, very unstable sample. Then the A delta NTU for the heat test was 38, difficult to stabilize, so much so that we needed 120 grams per hectoliter of bentonite or 130 grams per hectoliter of SMF. And you see that the delta NTU went very much down under the threshold of 2, which indicates stability. Then Manzoni Bianco. in this case, 71.8 milligrams per liter of total proteins. 10 is the value of instability. 100 grams bentonite, 90 grams of SMF were sufficient to stabilize. So you see that basically the quantity of bentonite is very similar to the quantity of SMF, with a difference of 10 to 15% more or less. In some cases, bentonite works a bit better or vice versa. So we have a similar amount of product to be used, and this is something that is very encouraging, we believe. All the data that I offered you were assessed on a small case dimension with additions which were in line with the laboratory approach. As Gianni said, the authorization process at OIV started a number of years ago. And every time when we presented data to OIV, the Techno-Scientific Committee answered by providing a number of recommendations in terms of additional data to be provided in order to make sure that the effectiveness is there and that it is precision winemaking, as Gianni explained. 2 large-scale studies were made, 10 hectoliters, one at IFV with Sauvignon Blanc and Crea Asti, and this is the second group with a Gewürztraminer, a much larger scale. And more difficulties because, of course, the scale is different.
Diverse cose.
You need to adjust a number of things. The results obtained have been very encouraging. For Sauvignon Blanc, 80 grams per hectoliter have been added in a discontinuous way, as is the case with bentonite, and it is not the application which is envisaged for this type of solution. Anyway, this is what has been done. This is the heat test. Different heat tests have been compared and contrasted because different companies, different countries use different tests. In blue, 40 degrees, 4 hours. In orange, 80 degrees, 30 minutes. Green, 80 degrees, 2 hours. Light blue, 35 degrees, 3 weeks. We saw that the sample, in all the original sample, the control, I mean, was unstable. And you see these various thresholds exceeding, in any case, the 2 threshold. So cloudiness was invariably the result. With the treatment with SMF, even with the stringent test, we proved that instability was very limited. Basically, full stability was obtained. If you then consider the other side of the question, in terms of the protein control post-treatment, we saw that reduction was by approximately 90% of total proteins with total elimination of chitinase and a residue of 15 of TLPs, 15 grams per liter. Second wine, second research center. So 2 independent studies, one in Italy, one in France. This is what was performed. This is the classic 80 degrees heat test. The control was highly unstable, more than 130 delta NTU in terms of response to heat stress. 70 grams per hectoliters of silica was added in the filtration process in a continuous way, and that accounted for full stability of the wine. You see here a number of data. A few of those that we produced. Here, electrophoresis is used to visualize the proteins in the control, in the test wine, before and after treatment. Here you see that the bands of the pure proteins have disappeared, which means that the silica retained those proteins also during the filtration process. Here we have a number of data produced over the course of time in order to try and test whether it is effective, this material. Well, we are convinced that it does work. It is effective in a way that is very similar to that of bentonite. What about specificity and the impact on the chemical composition of wines? I have lengthy tables of data about this, so I will refrain from showing them. But the pH, the alcohol content, the acidic composition, the sugar residue, glycerol, SO2, well, with reference to all the parameters I mentioned, we found no alteration. And it is to be expected in that it is a product that only binds with proteins, so why shouldn't it interact with these other components, let's say? Data have been found and produced on that, and that is encouraging. One thing has changed, though, and it is the analysis of metals, in that you see the composition have calcium, sodium, iron, and so on and so forth. You have the control sample with a specific profile of concentration of metals, and we made a comparison with two bentonites, bentonite A, 1 gram per liter, and bentonite B, 1.3 grams per liter, and SMF, 1.5 grams per liter. We know that bentonites release metals into the wine of various types. In some cases, in a significant degree, you see barium, for instance, has a major increase, while silica generally do not release metals. They are artificial products which have been properly cleaned before being used. In a number of cases, not only is there no release, but there is even a subtraction up to -10%, which can be significant for calcium and iron, especially when considering stability and oxidation. So there is a minor impact, and if there is an impact, then a reduction. Then effect on volatile compounds, control and bentonite and SMF. Each treatment has a minimum impact, and in this case, there has been an impact with reference to a number of volatile compounds in percentages which are highly limited. There is a minor reduction in the compound which is accountable for rose, for instance, and the same goes for fruitiness with ethyl octanoate, and no reduction basically in terms of citronellol or beta-phenyl ethyl acetate. Another parameter that we were asked to assess by OIV is the effect on the color of the wine. Rosé wines, in terms of vinification and composition, are similar to whites, of course, than red wines. So we made a spectrometric assessment of the three groups. Same concentration of bentonite and SMF, 50 grams per hectoliter. And we see that the outcomes are in line with those obtained with bentonite, which you see there, bentonite reduced by 8%, and in this case it is 6 or 8%, so a limited impact on rosé wines. Sustainability. This has already been mentioned by Gianni Triulzi. The advantage is that this is a material you can regenerate with the washing procedures that bring back the material to the original condition. You perform the treatment and then you regenerate. We have regenerated up to 5 times in our tests, but actually you can regenerate more, even more than that. There is a huge economic advantage in this respect because you reduce the cost of the solution. The solution can be used several times. Is it practical? Well, Gianni has already explained that the possible ways of usage are filtration or discontinuous. For the filtering process, whereby or rather which we focus on, this is a fast process. There is this filtering cartridge with silica, and the wine passes through this cartridge, and it is then exiting the cartridge deproteinized. Is it competitive? Is it cost-effective? The dosage, as you saw, is very similar to that of bentonite. There are, though, other economic aspects to be considered. Time. It is faster. You do not need to reflate the bentonite and wait for it to happen and then treat. And you can regenerate the used product. Plus, as Gianni said, no loss of wine. It is a negligible loss. You see, with bentonite, you have 3 to 5% of wines trapped in the lees, and that is a huge economic loss, while in this case, you do not have a loss. This is the major economic advantage. I'm about to conclude. The take-home messages are: functionalized mesoporous silica, evidenced to be effective in different areas with different varieties, different volumes, and with varying instability wines and vintages as well. We have had consistent results throughout, so we think that this can be a universal solution. We worked in the lab with just a few milliliters all the way up to hectoliters in an industrial setting, and data have been confirmed. Being a researcher who has been working in this field for years, I think I can say that this is a solution that can be very effective all over the world. With reference to additional advantages, please consider that it is a constant performance, it is a standardized material, while bentonite is collected from quarries. So it is a standardized material, no variation in performances, and no release of metals. In sensory terms, negligible impact. It can be regenerated, so it is sustainable in both environmental and economic terms. No losses of wine, which is key for costs. It is fast, no sedimentation has to take place. And basically, if you bring everything together, this is a solution that should be and entail a huge economic advantage for producers. Now I would like to give back the floor to Gianni to close our contribution, and I thank you very much for your attention.
Manca una piccola parte conclusiva.
I will conclude our contribution briefly. I will take just a few minutes. We have talked about this new material, which is functionalized mesoporous silica. It is new, and of course it is useful only if it meets the needs of today. Each solution has to be assessed in relation to what it can do for the current period. Let's consider some examples in relation to innovation as well. So we all know what this is. this indeed was innovative. It was a revolution, but it was 1800. And it was in the 19th century that in Wyoming, Montana, in that area of the United States, the first bentonite ore was found at Benton, which gave the name to bentonite, to this specific clay, which was then developed in terms of its application. So we talk about this century. This is something that was revolutionary at the time.
Possa fare un passo avanti.
I believe that we can add that research and innovation help us move on and forward. I want to say that this is what we have today. It is not that we use a different instrument or tool. We still talk about silica, but it is a silica which is updated, which meets current demands and needs. We expect performance which is not something that we can expect from a previous solution. This is what we can obtain from functionalized mesoporous silica. This passage from one situation to the other is possible because innovation exists. Innovation is performed by people with passion. Passion is fundamental if you want to innovate. There are so many people who have put passion into this project. I would like to thank Enartis people and staff specifically for that, and I would also like to thank the external collaborators at universities who help us with their expertise and skill to solve a number of issues. I would like also to thank the company itself, because Enartis has created the precondition for innovation. Innovation is part of the DNA of Enartis. Not only does Enartis favor innovation, but it also supports it. So it does create the conditions which are needed for all this to happen. Having said that, I thank you very much for your attention.